All right, so my name's Arushan, and I'll be presenting the feature selection and feature transformation workshop. So just to go over what's planned for this presentation, I'm going to quickly go over data preprocessing, and then go into feature transformation, and then into feature selection. So data preprocessing is an important part of machine learning, as the quality of the data that you're giving to the model directly impacts how the model learns and how efficient the model is. There's 4 parts to data preprocessing. There's data integration, data transform, data reduction, and then data cleaning. I'm only going to cover data transformation and data reduction, which is feature selection and data transformation, or feature search transformation. Jumping in right into feature transformation, we want to ask the question what it is. And feature transformation is a process of modifying your data but keeping the information. So it allows us to manipulate the data to increase the performance of our model. There are many machine learning techniques and methods to transfer data, like data normalization, data standardization, and hot encoding. Data normalization is a process of converting your a range of data from your numerical feature into a standard range, which is typically between 0 and 1. In the equation below, the minimum and maximum represents the minimum value that the feature can have and the minimum value the feature can have. And the x is just the input variable. Typically, it increases the speed for optimizing algorithms such as gradient descent. And then going on to the next slide, data standardization. This is a process in which we rescale the feature to have a mean of 1 and a standard deviation of 0, just like the image on the right. Going to the equation, the u or mu is the mean of the feature, and the denominator is the standard deviation of the feature. Jumping right into one-hot encoding. One-hot encoding is a process in which we convert categorical features into numerical features. This increases the dimensionality. However, this is actually a good thing to increase the dimensionality, since we don't want the model to think that the order matters in our categorical features. Looking at the image below, we can see that we have 3 colors, red, blue, and green, and they are represented as 1, 0, or red is represented as 1, 0, 0, blue is represented as 1, 0, 1, 0, and then green is represented as 0, 0, 1. And then we have a repeat of blue, which is the same value. And then moving into feature selection. So the primary reason or purpose of feature selection is to remove redundant features. So we want to get rid of features that are not useful in our models, and there's various techniques we can use. In the image below, we just as a high overview on what feature selection actually does is just we identify the useful features, and then we get rid of the non-useful features. So the benefits of feature selection. One of the big benefits of feature selection is that we reduce the dimensionality of our data. So we get rid of features that are not useful, and this way we can train we can improve our machine learning model by preventing overfitting. This typically also increases training speed because there's less data to train on, and then it also allows our model to become more explainable instead of having a really high dimensionality model that it'd be much harder to explain. So there's 2 types of feature selection. There's filter-based feature selection and wrapper feature selection. The filter-based feature selection works on a statistical correlation between the input and output features. It selects the feature selection scores each feature and then selects the highest or lowest score. An example of this filter-based feature selection would be Pearson correlation. Moving on to wrapper filter selection. So a wrapper works by creating multiple models with different subsets of inputs, feature inputs, and selects the model with the best performance, and that's determined by a performance metrics. Typically, that's accuracy, but there could be others. And an example of a wrapper feature selection would be a recursive feature elimination. And then jumping into Pearson coefficient as an example. Pearson coefficient coefficient is it's typically called an R value in stats. And we compute that by finding the covariance between two variables and dividing by the product of the standard deviations between the two. In the equation below, the x bar and y bar are the mean values of the two input features, and x and y are the input values. So the Pearson coefficient can have two, or it can range between -1 to 1. To have a positive correlation, both variables need to change in the same direction. And to have a neutral correlation, there's no change between the change. And to have a negative correlation, we need to have the variables to change in opposite directions. Typically, when we have high correlation, it indicates that they're linearly dependent, so we can get rid of one. So for example, if we have a high positive correlation, we can get rid of a feature that we're comparing to. Moving on to recursive feature elimination. RFEs are recursive feature elimination, or RFE is a feature selection method that wraps around a fitted model and removes the weakest feature or features until a specific number to a specific number we want. RFEs apply a backward selection process and ranking system to find the optimal combination of features, and the ranking system is based on the importance in which a feature's importance, which is determined by the coefficient. RFEs work really well on small data, and I will explain that, or small data sets, and I'll explain that in the next slide. So backward selection works by training a model with all of the features initially, and then finding the performance metrics, like typically, which is accuracy, and we see what the output is, and then we start taking out features, which is done by the least significant feature. And we then retrain the model and run the performance metrics and see how the performance increases or decreases. And then we keep continuing until we find the best set of features that will produce the best set of the best performance. And that's pretty much all I had. So thank you for listening, and we'll have officers next week from 7:30 to 8:30. All right. I think I could stop sharing.
Okay, everyone, I will continue with the code portion of this workshop as soon as Teams allows me to share my screen. All right. Can everyone see the Kaggle screen? Because I can no longer see Teams screen.
Yep, it's all set.
Awesome. So we're going to continue with the feature selection workshop for this code portion. So just as a review again, the quality of features used when building a machine learning model directly affects the quality of the model's predictions. So it's not always about what model you use, but what type of data you feed into the model. So with bad data, machine learning algorithms produce results that are inaccurate and incomprehensible. They have literally no reason to it. So in this workshop, we're exploring feature selection and transformation techniques that can be used to improve model quality and performance. So this notebook uses data information from these sources here, and some of the sources are linked down below. We're first going to do a little bit of data cleaning, just because that's a big part of machine learning. So we'll start with importing a data set, checking out the data set, and analyzing the data set using pair plots, removing null values, and removing outliers using the interquartile rule. Then we'll go into some feature transformation for normalization and standardization and one hot encoding. And finally, 2 examples of feature selection, with one using the filter method and one using the wrapper method. So first, I'm just going to import some useful libraries here, and we'll start with our cleaning. So in this problem domain, we're going to pretend that we are some startup that got funded to create a smartphone app that automatically identifies species of flowers based on pictures taken from a smartphone. So we were asked to create a demo machine learning model that takes 4 measurements from the flowers: sepal length, sepal width, petal length, and petal width. And we need to identify the species based on those measurements alone. So we've given a data set from our field researchers to develop the demo, which includes measurements of 3 types of the iris flowers: the iris setosa, the iris versicolor, and the iris virginica. So these 4 measurements we're using currently come from hand measurements by the field researchers, but they will be automatically measured by an image processing tool in the future. So first, we import our data set, and we can use this head method here to take a look at the first 5 rows of our data set. Here, it seems to be okay, but if we use the describe method down here, we can see that there are 5 values missing from petal width. So that's something that we're going to have to deal with later. So it's good to take a visual look at what we're trying to predict. And a good way to visualize how our data behaves is to look at some pair plots. So with these plots, we can see how each feature relates to the target variable and one another, right? So down on the left, we have all the features, and across the bottom as well. So in each of these plots, the y-axis is the feature on the left, and the x-axis is the feature on the bottom. And then down our diagonal row would be the histogram of the classes and for that feature. So in these pair plots, we can notice a couple things. One is, first thing is that we have 5 classes instead of the 3 classes that are expected. And there are some outliers and measurements that may be erroneous. So here, if we look at sepal length, we have these couple values that are close to 0, and that's really odd for the iris versicolor. So we might have to deal with that later. So first, we're going to fix the class labels. So apparently the researchers weren't consistent when they labeled. So they put versicolor for some of the iris versicolor. So we're going to change that to iris versicolor. And they misspelled setosa for some of them. So we're going to fix that. And once we do that, we will get our 3 classes like expected. So now we can redo our pair plots, should come up in a second, with our new 3 classes. So here we have our 3 classes, but now we still have those odd sepal length values and some outliers in the data. So yeah, 1 sepal width entry for iris setosa falls well outside its normal range, and several sepal length entries for iris versicolor are near 0 for some reason. So fixing outliers can be tricky, and it's never really clear whether an outlier was caused by a measurement error or recording the data in improper units, or if it's an anomaly. So for that reason, you should be really careful when you're working with outliers, because if we decide to exclude any data, we need to make sure that we document why we excluded it and provide solid reasoning. So in peer review, the data didn't fit my hypothesis is not necessarily a good reason. So in this case, the anomalous entry for iris setosa, let's say our field researchers tell us that it's absolutely impossible for iris setosa to have a sepal width below 2.5. So clearly this entry is made in error, and we're better off just scraping that entire entry than spending hours trying to fix it. So here we can see our histogram before, and we had that weird value. So we're going to drop that weird value right here by only keeping the iris setosa rows where the sepal width is greater than 2.5, which will give us this histogram of the data. And as we can see, everything is greater than 2.5. So the next issue is that we have several near zero sepal lengths for iris versicolor. So it kind of looks like, instead of recording these values in centimeters, it kind of looks like they're recorded in meters. So after some brief correspondence with field researchers, we find that one of them forgot to convert those measurements to centimeters. So we can do that here with this, this line here. So anything that is below 1 in value, we're going to multiply by 100 to convert it from meters to centimeters. And when we replot, we have decent values for that feature for that class. So now that we fixed that, we also know that there are a couple of rows with null or missing values. Now we can see that here that they're all of the class iris setosa. So dropping it may not be a good idea because this may bias our analysis since the missing data seems to be systematic. So one way to deal with missing data is to do something called mean imputation. So if we know the values for a measurement fall within a certain range, we can fill in those empty values with the average for that measurement. So here we can look at the range of iris setosa petal width values, and we can see that most of the widths fall between 0.2 and 0.3. So we can fill in those rows with the mean value. So here we get the mean value for iris setosa, and then any of those null values, we're going to fill in with the average petal width using this line here. So when we look at our data frame, we can see that those values have been filled in. So now it's always good to double check that what you did actually changed the data. And here we can see that nothing is printed for if anything is null. So that means nothing is null, and we fixed it. So here we can reprint or redraw our pair plot. And as we can see, we've cleared up some of the erroneous values and our null values and our clear outliers. So next, we're going to look into removing some outliers that are not so obvious from a pair plot. So there are many ways to remove outliers. And here we're going to employ the interquartile rule to remove those outliers. So this rule essentially is you calculate the quartiles, the first and the third quartile, and the interquartile range. And any value that is greater than 1.5 times the interquartile range added to the third quartile is an outlier. And any value that is less than 1.5 times the interquartile range subtracted from the first quartile is also an outlier. So if we use that rule on iris virginica class for the sepal length feature, we can see that we have one value here. So if we obviously know that that's an outlier, what we can do is we can drop it with this row here, or this code here, and then we can check that it's gone by checking if anything is out of the interquartile range, and we can see that there's nothing there, so we fixed it. So that's it for some data cleaning. Now we're going to look at normalization and standardization for our data transformation. So as Arushan said, there are kind of two options for feature transformation is to normalize or standardize your features. So normalization changes the range of your feature into 0 to 1 instead of whatever range it came in. So how you do that is you take the original value subtracted by the minimum value for that feature, and then divide it by the range for that feature. And that'll change it so that the minimum you can have is 0 and the maximum you can have is 1. And then standardization instead rescales your data so that it has a mean of 0 and a standard deviation of 1 for each feature. So what that does is it takes the value, then subtracts the mean of the feature, and then divides it by the standard deviation for the feature. So here I applied normalization. And for the sklearn package, Normalization is done by the min-max scalar. So they just called it the min-max scalar instead. So here we instantiate the scalar, and then we fit the scalar to our data. And all that is it's learning what the xmin and xmax are. And then we transform our data using those xmin and xmax, and we get a new data frame. And the scaled data frame, we can see when we do describe, we can look at the max, which is 1, and the minimum, which is 0, as expected. We can also apply standardization, which is called the standard scalar in sklearn. And once we transform our data here and describe, we can see that our mean is a really, really small number, basically 0. I mean, it's 10 to the negative 16, so basically 0. And then our standard deviation is very, very close to 1, as expected. So another thing for data transformation is hot encoding. So when we have methods that are not able to use categorical variables, explicitly, what we do is we change them into numerical variables so the model can use them. So how we do that is by hot encoding. So here we import this car data set. And what we can see from this car data set is that the fuel type is a categorical variable. If there are 3 different options for fuel type: CNG, diesel, and petrol. Now, let's say we were going to do a logistic regression classifier. We can't necessarily use the categories, the categorical variable on its own and give it to the logistic regression classifier. It's not going to work. So we can use hot encoding to change it from categorical to numerical. Here, all this code is doing is looking at the unique values of fuel type, which will list all the values, and then it's counting how many of each that we have. So we have 17 CNG, 155 diesel, and over 1,000 petrol. So we can convert the variable fuel type into 3 numerical variables. We're going to call each of the 3 the actual original fuel type. So there'll be 1 column CNG, 1 column that's diesel, and 1 column that's petrol. So we assign the new variable CNG to 1 when that is true for that example, and diesel and petrol are 0. And then when it's actually a diesel car, then diesel is 1, and CNG and petrol are 0. And then finally for petrol, when it's actually a petrol car, petrol is 1, and CNG and diesel are 0. So what that does is then we end up with a fuel type. The fuel types are these 3 columns, and we can see, if it's diesel, we have 1s here. If it's petrol, we have 1s here, and so on and so forth. So to do that, we use this get dummies function from pandas, and that just does the hot encoding for you. So we can add that, we can add those 3 rows to our original car data set and then drop the categorical fuel type column. And then we get this new data frame where fuel type is gone, but we have our rows for CNG, diesel, and petrol. And then this is something that we could actually give a classifier like logistic regression to actually learn a model from. And then we have some feature selection options. So first, we're going to look at wrapper methods and then filter methods at the end. So this paragraph here was taken from sklearn, but basically sequential feature selection is a wrapper method, and it's a greedy procedure that iteratively finds the best new feature to add to a set of features. So they initially start with 0 features, and then they find the 1 feature that maximizes a cross-validated score when an estimator is trained on that single feature. So they'll start with 0 and then try each of the options of features, and whichever one gives them the best score is that 1 feature. And then once the first feature selection is selected, they repeat that procedure by adding new features to their selected set of features. And then they stop when they reach the desired number of features. So backward sequential feature selection is the same idea, but in reverse. So they start with all of the features, and then they drop 1 feature at a time, checking their score and seeing which feature to drop that will give them the highest score. So in general, backward and forward selection do not actually yield the same results. Also, one may be faster than the other depending on the requested number of features. So if you have 10 features and you want 7, if you do backward forward selection, it will be faster than forward selection because going from 10 to 7 is much faster than going from 0 to 7. So here, we're just going to reload this Boston data set. Doesn't really matter what the data set is doing. We're just going to use it for filtering. So let me run this here. And then the target variable is price. So here's this, the first 5 rows of our data frame, and our target variable is price. So we are going to apply forward selection. And all this is doing is it's iterating using sequential feature selection, doing forward selection, and it's printing out the feature and the time that it took. And then here is backward selection. Now, the thing to look at when we compare these two is that for one feature, it picks the same thing for 2 features, both backward and forward selection pick the same 2 features. But if we look at 3, we actually get a different amount, or the 3 like one of the features is different from over here. And that just goes to show that backward and forward sequential feature selection don't always give you the same results. Also, if we look at the time that it took, right, for forward feature selection, it only took 0.1 seconds to get 1 feature. But for the backward selection, it took 0.8. And that's because backward feature selection had to start with the original 13 and then drop down to 1, whereas forward selection started with none and only had to pick the best one. And then the opposite is true when we look at 12, right? So 12, the backward feature selection started with 13, only had to drop 1, so it took 0.1 seconds. But forward feature selection started with 0 and had to go up to 12, so it took about 0.8 seconds. So then here we can look at the filter method. So there are kind of 2 ways to use this filter method. So what you can do is we are going to use Pearson correlation coefficient as our parameter to filter by. So for data frames in pandas, they have this correlation function that default uses Pearson correlation coefficient, and you get this matrix that'll tell you the correlation between the row and the column labels. And what we care about the most is the correlation between price and all of the features. So basically this column here. So you could use price, or this column of correlations to see which feature is the most correlated with price, and that could help you decide which feature you want to use. Or you can see which features are the most correlated with each other, and then you kind of just drop one. So here we're going to look at the features that are most correlated with price, and then that's the one that we will preferentially keep. So with this line here, we're just going to select this last column here, and then we're going to rank it in order of the absolute value of its correlation, because having a correlation of 1 and having a correlation of -1 are both equally useful when we do machine learning. So, here, when we rank them, we can see that this LSTAT is very useful, and this feature right here is not that useful. So, we'll run that. And then we can preferentially choose this LSTAT instead of the other features, and then kind of go down in order for how many ever features you want. So here, all that's doing is if we want 1 feature, we're just going to take this LSTAT feature, and that's the accuracy we get. If we want 2 features, we're going to take the top 2, and that's the accuracy we get, and so on and so forth. And the interesting thing here is that with the 1 feature, we get an accuracy of about 54%, which is not necessarily terrible for a regression. But if we compare 3 features to about 10 features, we can see that the accuracy doesn't increase that much, meaning that these 6 features in between were not that useful. But That's all that I have for the code for today. Make sure to check us out on Facebook, Instagram, and on our website.